Alrighty. I'm recording this on Halloween, though I doubt you are watching this on Halloween. But happy spooky Halloween from space. We have the sun as our big glowing jack-o'-lantern, and then the ghost galaxy, which is actually two galaxies that are undergoing a merger. But kind of looks like a specter. All right, we continue on now. Actually, let's get a little bit more quantitative, less me telling stories about Newton's law of universal gravitation. Everything we're about to learn, really, there's nothing new besides that we're just learning a new, different way of how to write down this particular force in order to solve more general problems that involve gravity and don't restrict us to just being super close to the Earth. We will actually see where little g comes from today, but we might be interested in doing problems that don't involve us being within, a few thousand meters or so of the surface of the Earth. So what Isaac Newton did is his study of universal gravitation, once he realized that there was this single gravitational force where objects with mass appear to exert pulls towards one another, like apples falling towards the ground, like the moon falling and missing and orbiting around the Earth, the sun orbiting around, or the Earth orbiting around the sun. He set up a series of experiments where he studied how these variables depended on one another. And so he would do things like set up two particular balls of mass. One of them might be attached to, say, like a torsion wheel, so it would essentially be like a big rubber band. And the masses would be pulled ever so slightly towards one another because of their gravitational tug, and he would measure the amount of deflection that would occur as a result of them being pulled towards one another, while one of them would be allowed to, say, twist on a vertical rubber band that could, that essentially could be treated like a spring. More sophisticated versions of this experiment was how he actually determined this overall gravitational constant. But Newton was able to, through kind of thought experiments and little experiments like that, reason out that the dependence of this force due to gravity, I've written it out above, but let me just write it out again, that this force due to gravity he was able to find is proportional to the masses of the two objects. So if you have some object M1 and some object M2, they will pull on one another with an equal and opposite amount of force. Newton's third law, of course. That force appears to depend not only on the masses of the object, both of them have to have some non-zero mass, and the amount of force seems to depend on the product of the two. But then by changing the distance between them and measuring the amount of force, Ray concluded that it should go as the inverse square of the distance separating the 2 point particles. So this is an example of an inverse square law. Which simply means it's a law that depends on the inverse square of the distance between the two objects. You will see this week 1 of Physics 3, Coulomb's law, which says the force between two charges is some constant charge 1, charge 2 divided by the distance squared. That is Coulomb's law for electrostatics. It is also an example of an inverse square law. So the idea behind proportionalities is if something is proportional to another thing, that means they are related by some constant that does not depend on m1, m2, and d squared. So we now use the letter capital G to correspond to that constant. So we write Newton's law of universal gravitation is gmm over d squared. Newton actually never measured g. He never actually had a number for g, let alone call it Newton's constant, as we sometimes call it now. But he was able to reason out the proportionality and still use that to, prove Kepler's third laws and prove what an orbit is and do all of his deductions without even knowing the value of g. a lot of that he could reason out through ratios, which is something we'll do later in this class. It's a very helpful technique because ratios often allow you to not need to look up, the values of these sorts of constants, because this capital G, it's not 9.8, but it is 6.67 times 10 to the minus 11, which itself is pretty small, and then has units of newtons meter squared per kilogram squared. It has some weird combination of mixed units, which, notice, if you take G and multiply it by 2 m's, that cancels out the kilogram squared in the denominator. Then if you divide it by a distance squared, that cancels out the meter squared in the numerator. You are left over with something that is units of newtons, a force, as must be the case. Units never lie. And I'm comfortable saying that this is a fairly small number. Small numbers are always relative because I could always change my units to make the number, as big or as small as I want. I could do this in, newtons per, light years squared divided by grams squared or something, and that would make that would change the value of this unit, for example. That would actually make it smaller, actually, but this is a fairly small number, and it ties into the fact that gravity is one of the weakest forces in the universe. Essentially, there are 4 forces that determine everything. If you understand the 4 fundamental forces, every other force is some combination or interpretation of these 4 forces. And the 4 forces are gravity, electromagnetism, physics 3, and then the strong and the weak nuclear forces, which are forces that govern what goes on inside nuclei and what goes on inside electrons and protons and whatnot. The strong and the weak nuclear forces the strong nuclear force is the strongest of the 4, but its range is very, very small. It becomes very ineffective outside the nuclei of atoms. Electromagnetism is kind of the second in line, but requires that things have a net charge. That will be most of physics 3. If everything is electrically neutral, the electromagnetism forces do not play a significant role. Similarly, the weak nuclear force is weak, and also its effect goes away very quickly once you get to distances outside, say, the sizes of electrons and protons and whatnot. Which leaves gravity left over, which is also fairly weak, but only requires mass in order for this force to be present. Which is why on the largest scales, like space in the universe, this is the one force that does most of the tugging, the pushes, and the pulls. On average, space is electrically neutral, and space is hella big. So the nuclear forces don't do anything, and the electromagnetic force doesn't do anything, leaving gravity to be the dominant force for most of astrophysics. So let's see, this is defined, I wrote this as a vector, but the vector notation can get a little tricky to imagine, especially when you're dealing with things that are, say, orbiting one another, or are moving around in very complicated paths. So I would say, in this class, it will suffice if you just explain the vector notation in words. Everything will likely be forces will be perpendicular to one another, or all kind of add up in a line. It will be very clear how the forces are supposed to add combine with one another. But I would say, focus still on the conceptual idea that the gravitational force pulls on each object with an equal and opposite amount of force. So this particle over here, if this is M1, it is pulling M2 towards M1. Similarly, M2 is pulling M1 towards M2. So if I were to release these particles from rest, they would likely, come together somewhere in the center, depending on, how easily they are able to move. And the magnitude of this force, if I wanted to evaluate the magnitude of this force, I would take big G, plug in their masses, and then I would have to calculate this distance squared, which if I have something like coordinates, one's at 1, 2, the other's at 3, 1, just to review, if R1 is 1, 2, if R2 is 3, 1, then the distance between them would be the magnitude of their difference, which in this case would be something like 1 minus 3 is negative 2 squared is 4, and then 2 minus 1 is 1, squared is 1. So this might be something like the square root of 5 meters or something like that. So therefore d squared is just going to be 5 meters squared. So then I would just plug that in to my expression to get an actual magnitude for the force. And if I wanted to think of this in terms of vectors, I would just have to remind myself that this is the force points in the direction toward the individual objects. M1 pulls on M2 by pulling it towards itself. M2 pulls on M1 by pulling it towards itself. Equal and opposite direction, satisfying Newton's third law, as it must. But it is a mutual gravitational interaction with each other. So in this case, the idea now, we've only been dealing with gravity in terms of the Earth and some object, an apple that I drop towards the surface of the Earth, for example. We've only been dealing with two objects, right? The Earth was tugging on the apple, and again, we knew this by Newton's third law, but we can say it again now. The apple also pulls down on the Earth, or pulls up on the Earth, rather. But what if you have multiple objects? Suppose you have the solar system. You have, the sun at the center. You have Mercury. You have Venus. You have Earth, which itself has a moon. You have Mars, which has 2 little moons, and then you have Jupiter, which has, it's up to like 70 or something moons right now. And all of these individual objects, if I were to look at, the sun's pulling on Mercury, it's pulling on Venus, it's pulling on Earth, it's pulling on Mars, it's pulling on Earth's moon, it's pulling on Jupiter, it's pulling on Io, Europa, Ganymede, Callisto, all the various moons of Jupiter. And I could keep going. There's all of these gravitational tugs on the sun, for example. All of the planets, all of the moons are also tugging on the sun. So what if I wanted to analyze, what direction the sun moves in because of the planets and the moons? And then maybe, right, there's that asteroid belt that has a bunch of stuff in between Mars and Jupiter. They are also tugging on the sun. Each one of those rocks is tugging on the sun, and the sun is tugging on them. How do I incorporate some semblance of the net gravitational force that is pulling on these objects? Well, gravity obeys something which is called the superposition principle. That is not how you spell principle. Which simply says that the net gravitational force is the sum of the individual gravitational forces. If I want to figure out the net gravitational force on the object, I just add up all the individual tugs that object is experiencing. Now you might be wondering why this is not new, you might be thinking. This is not new at all. We did this when we did Newton's laws. The net force on an object equals the mass times acceleration. You add up all the forces and look at how they in net contribute to the object's motion. But the superposition principle is actually saying something a little more profound, because up to this point, we've only been dealing with kind of one gravitational force and then a bunch of contact forces. This ball is in contact with the table and is also feeling gravity pull down. So, and we look at the net force by adding the one gravitational force with any of the contact forces, right, which could also be other forces as a result. I just took a snapshot of myself from the apple. But we never had to consider that there could be multiple gravitational forces pulling on the object from different gravitating bodies. Earth, the moon, Jupiter, all these things. So the idea that you're able to write down that the net force from gravity is just the individual sums, where you don't actually have to worry about any sort of, that it just adds, we would say that the forces add linearly. Right, that F1 gravity plus F2 gravity. Right, you just add them with a simple addition sign in between them. So you could look at each of them individually and get an answer. That's different than if it was something like F1g squared plus F2g squared, all in the square root. That is not a linear combination in that case. You have to square it, and then you add them up, and then you take a square root. In this case, something like this actually favors the larger forces. It's biased towards the larger forces compared to a linear combination where every force is treated on equal footing. So the idea of superposition, again, nothing new really. But the fact that we're able to show that this holds with long-range forces like gravity actually works into our understanding of how these long-range forces work. That they are acting, each of these individual tugs and pulls, which is occurring, across, a vacuum across the air, is occurring, without any sort of weird overlapping interference or interaction with themselves. Which is not the case, for example, in things like quantum mechanics, where you can have entanglement, where you can get weird kind of mutual interactions across various objects and forces. So in this case, let's look at a couple conceptual problems. Suppose I have some concentric rings, and they're each spaced 10 meters in radius. So the first one is 10 meters in radius from the center. The second one is 20 meters in radius from the center. And there are three objects that are shown as green circles. If I were to hang out right at the origin, what is the net gravitational force that I would feel on myself? Or in this case, what is the net acceleration that I would feel on myself? So in this case, I would say that I do feel a net gravitational pull, but it is directly towards the left, towards this object. The other objects are still there, but when I'm located right at the center, this particle is symmetrically opposite this particle. And so I'm being pulled in one direction by a force, but then I'm being pulled in the other direction by the same amount of force. By the superposition principle, the ones along the diagonal will cancel out while I'm right at the center. Once I shift over to the left a little bit, like where my mouse is, then it's not symmetric, and then I might feel myself pulled a little bit, upward, because I'm closer to these objects than this object. Because again, the idea is that I can write the net force on me. By the superposition principle, I can just write that as the net sum of all the individual gravitational forces, and then set that to my mass times my resulting acceleration. So in this case, I had three gravitational forces pulling on me, and then that equals, these are all gravity, that all equaled my mass times my acceleration. But by symmetry, this object, which has the same mass as this object, and is the same distance away from me, and is in the opposite location relative to the center. You know, if we called that, maybe that was force 1 and force 2, they would end up canceling each other out while I'm at the center. And so as a result, the gravitational force on me would be gm, my mass m, divided by, I think I said 10 meters squared. And that equals my mass times my acceleration. This is pointing to the left. I'm being pulled towards the object on the left. My mass cancels, just like what we saw with gravity. You know, that was Galileo's kind of Pisa experiment. The mass does not matter. Your mass does not matter because it cancels out in both the gravity term and the ma term. And then I think I said this was 1. I could look up g. I could plug this in and get a number. What about this setup? And again, just looking for you to tell me, what is my net gravitational acceleration when I'm located at the center? So in this case, I would say, okay, this particle is canceled out by this particle. They're pulling me in opposite directions. This particle is canceled out by this particle. They're pulling me in opposite directions. This outside particle is canceled by this outside particle because they are pulling in opposite directions and are the same distance away. Right? It would be incorrect to say this particle, the one on the far left, cancels out the inner one on the right because they are different distances away from me at the center. Gravity depends not only on the masses, but on the square of the distance between me and the object. This particle exerts less of a gravitational pull on me from the center compared to this particle because it's closer. But these two cancel these two. This one cancels this one. Everything is canceled except this one in the upper right, so I feel myself pulled initially diagonally up to the right with a weaker amount of force because I'm being pulled by an object that's farther away. Last one. So in this case, these inner two are canceled by these inner two again. This left one is canceled by this right one. This upper diagonal right one is canceled by this lower left one. This top one is canceled by this bottom one. So the only thing that's left is this guy up here. So I would say in that case, I feel myself pulled towards the upper left by just, as if it was just this one single particle. I feel a force. Let me do a copy and paste real quick. Should have moved this over first. Oh dear. When I'm located at the center, these cancel each other, these cancel each other, these cancel each other, these cancel each other, these cancel each other. When I'm located at the center, both of these give the same answer for my overall net acceleration. Most of these cancel each other out, and I'm left with a net acceleration from this object, as if that were the only object around. All the others are equal and opposite in direction. All right. That is the idea behind superposition, which again, might not seem like anything new, but the fact that we can also say it for gravity, this long-range force, is perhaps a little bit more profound than what meets the eye. Thinking of this in terms of extended objects. Now, this is not a point particle. This has many, many point particles. And you might think maybe we can represent it as if the object was completely located at the center of mass. We will be able to say something like that. And then it falls towards the Earth. The Earth itself is not a point particle. So if I wanted to use Newton's law of gravitation his universal version, where it's gmm over d squared. If I want to use that to measure the acceleration of this apple as it falls towards the Earth, some of these it's clear what I should use. G I could look up in a book. Right, M I might use the mass of the Earth. M2 I might use the mass of the apple if I'm measuring the apple falling towards the Earth. But then what do I use for D? If I hold this 2 meters above the ground and drop it, do I use 2 meters or do I use something else? Now, thinking of the idea that we can replace an extended object as if it was all located at the center of mass, that gives us a clue as to what we are able to do for these massive extended objects. Particularly, we're going to focus on objects that have spherical symmetry. So this is for So this might be uniform spheres. This might be a shell, an actual hollow shell, but it is in the shape of a sphere. It could be a bunch of concentric shells where each of them have a different mass, but it's nonetheless, each of them individually are spherically symmetric. Like the Earth, we could take as spherically symmetric, even though as I go deeper into the Earth, the density of the ground changes, and so there's a different amount of mass at every shell as I go down. But we could still treat the Earth as spherically symmetric. And you could think of it as a bunch of concentric, like a Russian nesting doll of shells, where each one is slightly different. And so Newton proved this with geometry. It would take a little bit of Calc 2 for me to prove this. So I encourage you to go look at the Wikipedia article for the shell theorem, which walks through the proof, but it involves some polar coordinates and some changes of variables that some of you have not seen yet. But this says, or you could try to prove it geometrically as Newton did, which was the more hardcore way. But then you have to be really good at geometry. So what they found, what these proofs show, is that for spherically symmetric objects, the gravitational force they exert on an object outside, I'm out of space. I'll copy and paste this over. For spherically symmetric objects, the gravitational force they exert on an object outside of it, so outside the shell, outside the sphere, is as if all the mass were concentrated at the center. You find your penmanship varies wildly depending on like the time of day or likely the amount of caffeine in my system. Sometimes my penmanship is beautiful. Sometimes it looks like this, and I apologize. For spherically symmetric objects, the gravitational force that it exerts on a different object, so suppose I have something like the Earth, and then I have a ball that is over here, some distance away from the Earth. So there's some distance here, we'll call it maybe the height it is off the ground, but then the Earth itself also has some radius of the Earth. If I wanted to ask, what is the gravitational force on the Earth from the ball? No. What is the, well, yes, but what is the gravitational force on the ball from the Earth, which is also the same as the ball on the Earth by Newton's third law? What the gravitational force of this big extended Earth is pulling on the ball. The way I could calculate that is I could imagine, instead of an extended object of the Earth, as long as it's a nice symmetric sphere, I could imagine as if the entire thing were concentrated right at the center of the Earth. And then I get rid of this. I don't care so much about the actual Earth, but I just imagine it's a point particle located at the center of the Earth. And then the distance I plug in, then I could plug in G, M Earth, M apple, M ball, whatever it is. And then I plug in D squared in this case. Where for this particular example, D equals the radius of the Earth plus the height off the ground. So you don't use the height from the floor. I don't use 2 meters to calculate the gravitational force. I imagine as if the entire Earth were concentrated as a point located at the core of the Earth, 4,000 miles away from my feet. And what I plug in to the gravitational equation for GMM over D squared, for D I plug in not the height it is off the ground, but the height off the ground plus the radius of the Earth. For the sun, and this is true if both objects are spheres. Take the sun and the Earth. The sun has some radius equal to the radius of the Earth. The Earth has some radius equal to its radius. And if I wanted to ask what is the gravitational force between the sun and the Earth, I would not look surface to surface. I would draw a line from the center of the sun to the center of the Earth, and that is what I would use for D. Center to center. Right. Gravitational forces are measured center to center. Turns out if you're inside the shell, the net gravitational force is 0, no matter where you are inside the shell. But I'll leave that for Physics 3, where you'll prove that with electromagnetism. But for us, we're always going to be outside the surface because it's always going to be planets or stars or whatnot that we're thinking about, or balls above the Earth. So again, for the ball example, if this were a perfect sphere, which is not, I would use the center of the sphere and draw a line between the center of the sphere all the way down to the center of the Earth. And that is the distance I would measure. And plug into the gravitational equation. Suppose we are near the center of the surface of the Earth. So here's the surface. Here's some ball, or an apple. We'll stick with the apple. And it has some height h off the ground, which is much, much smaller compared to the radius of the Earth. H might be 2 meters, where the radius of the Earth is more like 4,000 miles or so. So 6,000-ish kilometers or whatnot. So h is very small compared to the radius of the Earth. And I want to ask myself, if I were to let the object go, what is the acceleration that it feels from the gravity of the Earth pulling down on it? You might say m little g. Let's not take that as a given. Let's use the universal law of gravitation to write this down. So if I define up as positive, I might say that the sum of the forces acting on the apple equals the mass of the apple times the acceleration of the apple. If I'm only considering the gravitational force, then this is pulling down at some rate minus g, m Earth, m apple, divided by, in this case, again, center to center. So I might write this as the radius of the Earth plus the height off the surface squared equals m apple, the acceleration of the apple. M apples cancel. It's nice. And I'm going to make the approximation that since I'm near the surface of the Earth, h is much, much less than the radius of the Earth. 2 meters compared to 6,000 kilometers. So that's as if I'm taking a really big number and adding on to it a little bit. So I'm going to approximate this simply as the radius of the Earth. If I'm near the surface of the Earth, then the height off the ground is very small compared to the actual radius of the Earth. I can make this approximation without significant error. Again, this is the idea of you have $1 million and I give you a penny, you essentially still have $1 million. That then implies that A of the apple equals minus g m Earth divided by the radius of the Earth squared. We know the radius of the Earth. We know the mass of the Earth. We know the value of big G. We could look these up. Any guesses at what value it equals? It evaluates to 9.8 meters per second squared. The origin of 9.8 meters per second squared is that it is the mass of the Earth pulling down on the object, and that object is roughly the radius of the Earth away from the center. So g m Earth over r Earth squared is approximately little g. That is where 9.8 meters per second squared comes from. And what allowed us, by the approximation that the height above the surface was small, which was always the assumption we were making, what that allows us to do in this case is say that the local acceleration is approximately 9.8 meters per second squared as gravity of the Earth pulls down on any object. Sometimes this is called the surface gravity. Where if you wanted to say find the surface gravity on the moon, you would do big G m of the moon divided by the radius of the moon squared. And you would get something that's about 16%, 9.8. If you wanted to do the surface gravity of the sun, you'd plug g m sun squared divided by the radius of the sun squared. It's the same Newton's second law setup. You hold the apple a slight distance above whatever surface. It is being pulled down by some amount of mass that is some distance away. So it's the same sort of setup for any planet or star or whatnot. But this also allows us to say things for, for objects that are not really close to the surface of the Earth. The Hubble Space Telescope. Is about 350 miles above the surface. So I could ask, what is the acceleration? It clearly is feeling a gravitational pull downward from the Earth. Now it does not crash into the Earth because it also has that velocity, going back to the last lecture. It's constantly falling towards the Earth but missing. But I could ask, what is this acceleration? It is not 9.8. The free body diagram is that the Hubble Space Telescope is being pulled down by a force due to gravity from the Earth. And that's it. So in that case, if I define up as positive, F equals ma, so F of gravity equals the mass of Hubble times the acceleration of Hubble. That implies that it's minus g. What are the two objects pulling on one another? It's the Earth and Hubble. But now the Hubble is located not at the radius of the Earth, but it's a, if we call this h, it's located at the radius of the Earth plus 350 miles, which is still less than 4,000, but it's not tiny compared to 4,000. It's approaching 10%. And then that is mass of the Hubble, acceleration of Hubble. Again, the mass of the scope itself I do not care about. If I were to plug all these numbers in, I would get something that is about 8.27 meters per second squared equals the acceleration of Hubble. It is feeling a gravitational acceleration, not 9.8, but about 8.2, 8.3 or so. What about the moon? The moon is also being pulled towards the Earth. It, of course, is missing the Earth because it has its own velocity. But I could do the same problem. Again, it would be negative g in this case, m Earth, m moon, divided by, again, thinking of what distances do we think about here? It's center to center. So it's whatever is the distance between the center of the Earth all the way out to the center of the moon is d. D in this case is about 250,000 miles. Which perhaps gives some context of why it takes astronauts several days after launch to get to the moon. So then we would plug in, 250,000 miles squared for the denominator. And then that's equal to the mass of the moon times the acceleration of the moon. The moon mass goes away. The acceleration of the moon, in this case, is something 0.002 meters per second squared. The moon feels an acceleration towards the Earth, but not 9.8. But more like 2 times 10 to the minus 3 meters per second squared. And just so there's no confusion, this is not the acceleration you would feel on the surface of the moon. The moon surface acceleration would be something like g m moon divided by the radius of the moon squared, which is something like, like 1 point something, I think. This is the acceleration from the Earth on the moon. The moon feels itself accelerated towards the Earth at 0.002 meters per second squared. By Newton's third law, the Earth feels itself accelerated towards the moon at 0.002 meters per second squared. But given that the Earth weighs, several times, factors of 10 more than the moon appears to be doing all the motion. You have the Earth, and you have the sun. The Earth is going around in an approximate circular orbit. The distance between the Earth and the sun is well established. We call it 1 astronomical unit, or 1 AU. And it is about 1.5 times 10 to the 11 meters. 93 million miles. Mass of the Earth, mass of the Sun, you can look up. And the question is, what is the speed that the Earth is moving around the Sun? A lot of these gravity questions deal with circular motion. So it's a good review of circular motion. So in this case, I would ask, what are the forces acting on the Earth? What is my free body diagram for the Earth? In this case, it's feeling itself pulled by a force of gravity due to the Sun. And that's it. Though we also know there's circular motion. So then if I define towards the Sun as positive, I might say that F equals ma is g m Sun m Earth divided by this distance squared, this 1 astronomical unit. And that equals the mass of the Earth times the acceleration of the Earth. Newton's second law. But if it's circular motion, particularly uniform circular motion, then this is v squared over, not v squared over r, sorry, v squared over d for uniform circular motion. In this case, the mass of the Earth cancels. One of the d's cancel. And you get that the velocity of the Earth is the square root of g m Sun times 1 astronomical unit. Which, if you plug in the numbers, it's about 30 kilometers per second. Again, nothing really that sophisticated. It's still just, we are doing Newton's laws, but now we just have a new force that we can play around with. So we have more options in terms of the number of equations we can do. What about the period of the Earth around the Sun? Well, if we know the distance it is from the Sun, we know the circumference of its orbit. We know that it's moving at some velocity v, so we know that it has to go 2 pi d worth of distance, and it's doing so at some velocity v that we just solved for. And this is, the period for circular motion. Again, review. We've seen this before. That implies that t equals 2 pi d, and then this was root g m Sun over d, all in the square root. Unsurprisingly, I could plug all these numbers in. I get 365 days, or a year. But if I keep this as symbols, and then I square both sides. So let me square both sides. So then the numerator becomes 4 pi squared d squared. The denominator becomes g, just the square root goes away. I could rearrange the bottom part. It's a fraction of fractions, so I flip and multiply. I get something that looks like this. Particularly, I get that the period squared goes as 4 pi squared, the distance cubed, the distance between the Sun and the Earth cubed, divided by g, mass of the Sun. This actually is how you prove Kepler's third law. Let me go back to the slide that showed that from previous lecture. Recall Kepler had come up with these 3 laws of planetary motion. His third one said that the square of the planet's orbital period is proportional to the cube of the orbit's semi-major axis, or you can think of this as the radius of the orbit. So Kepler had claimed that, he's using P, we've been using T. Those are images, so I can't edit them. So he said essentially that T squared equals K D cubed, which is exactly what we just showed, that T squared equals some constant, this thing right here is the constant K. It depends only on the mass of the sun, which is not changing. For circular motion, there is a quite simple relationship between the square of the period and the cube of the radius of the orbit. So again, to remind us, period, radius of orbit, sometimes called the semi-major axis, and then we have mass of sun. Which is actually kind of nice. For this particular problem, when I had solved this above, I had taken the mass of the sun as a given, and we had figured out what was the velocity and what was the period given the mass of the sun. This is actually how we determine the mass of the sun. We do the problem essentially, but we do it backwards. We can measure how long it takes the Earth to go around the sun. We essentially just look until we see the night sky repeating itself, and we know we've completed 1 full orbit around the sun. So we know the square of the period. We can use essentially triangulation between the Earth and Venus and the sun to calculate the distance between the sun and the Earth. So if I know T and I know D and I know 4 and pi and G, you can solve for the mass of the sun. And that is our best measure of how we know the mass of the sun. We can't go and take the sun and put it on a scale, what that even means, because a scale assumes, there's a gravitational field. How do you measure the mass of, objects like the sun? It's exactly through using something like this, Kepler's third law. You can do this experiment as well with Jupiter's moons. You could redo this entire problem, but instead of Earth and the sun, do it for, Ganymede and Jupiter. You get a Kepler's third law equation like this, but instead of the mass of the sun, in the center, it's the mass of Jupiter. It's the mass of whatever is the big central object. And you could, with a good pair of binoculars, make some measurements and calculate Jupiter's mass to a few percent, actually. What if you have 2 stars orbiting each other? Sometimes called a binary star system. So I have 2 stars, and let's suppose they're both the same mass. And they're orbiting around in a circle. And going back to chapter whatever it was, they would orbit if there's no other external forces, they would orbit around their common center of mass. They would orbit around their tipping point, which is just going to be in the center. And suppose that distance to the center of mass is d. I could ask, what is the velocity of each star as they move around in circular motion? Here you have to be careful with what you plug in. So let's take the one on the right. The free body diagram says that there's some gravitational force pulling it to the left, given where it's at right now in this drawing. It will always be pointing towards the other star, wherever it is, as they move around in a circle. So then I would say that the gravitational force in this case is something like G m over center to center, the distance between them squared, which in this case is 2d squared. That equals the mass of one of the stars times its resulting acceleration. But if it's in uniform circular motion, I can write this as mv squared over not 2d, but just d. Because for circular motion, you're doing it relative to the center of the circle. The radius of this circle is d, though they are separated by 2d. Anyway, the mass cancels. One of the d's still cancel. Well, what happens over here? This becomes gm over, looks like 4d squared, and then that equals v squared over d. One of the d's cancel. In this case, it looks like you get that v equals the square root of gm over 4d. Or, to simplify the square root, 1/2 gm over d. So it's not just gm over d like we saw before, but it's 1/2 that as a result. Where d, we just have to be careful, where d is measured from the object to the center of the circle, not between object to object. You just got to be careful with your symbols. Now let's see, I wanted to do a little bit of energy in Kepler's second law. But I think I'll save that for the beginning of the next lecture. Right now I want to do some ratio examples. So in a lot of those examples, it required us to look up the value of g, which I did in advance. You're not going to watch me plug things into a calculator. The capital G is tedious, 6.67 times 10 to the minus 11. And you got to be careful that all your units match. But there are problems where you can ask yourself what's going on and actually calculate stuff without ever needing to know what little g is, or big G rather, sorry. Take this as an example. All right, two particles with mass m are a distance d away from each other. If d is tripled, then the gravitational force between the two objects increases, decreases, and does it increase or decrease by a factor of 3 or by a factor of 9? I guess they're both the same mass m. I could have made these the same object. Now what you could do is you could say, okay, I'm going to set m to be, say, 5 kilograms for each of them. And then I'm going to say d is equal to 20 meters, and that's going to triple to 60 meters. And I could plug in all the numbers and compare what the forces look like originally, and then compare what the forces look like after the distance is tripled. And you would, of course, get the right answer. But the number of opportunities for you to make a math mistake in that case is incredibly high. And involves you having to deal with annoying things, like looking up little g. Big G. So used to little g. Instead, we can do this via ratios. So with ratios, you essentially write down an expression for this gravitational force. So I have the gravitational force originally, which was g m over d squared. And then you have g, the force due to gravity final, which was something like g m, the masses aren't changing, but the distance is tripling. So I might say 3d squared instead. D increases by a factor of 3. And the idea behind ratios is I could look at what is the ratio of the final total amount of force to the original amount of force. And we'll see that this is useful because it's going to make a bunch of things cancel out as a result. I can simply just plug in the expression. So I have gmm over 3d squared. Then the denominator is gmm over d squared. I have a fraction of fractions. So I could take that as I could take the bottom one, which I'll multiply that out, so that's 9d squared. Then I flip the bottom one and multiply that, so it becomes d squared over gmm. And look what happens. M's on the top, m's on the bottom, gone. D squared's on the top, d squared's on the bottom, gone. And g on the top, g on the bottom, gone. The answer is just 1/9. So then if I follow the equalities, this says that the final gravitational force equals 1/9 the original gravitational force. So in this case, I would say it decreases by a factor of 9. You can do this for any sets of equations. It's not just the gravitational equation, though this is a great example because it shows how by doing if you're doing a comparison, the way in my physics 90 class I always say is that if you ever hear the word compare, you should immediately think take a ratio. Because they will almost always, I structure my physics 90 class so that they never once have to plug in big G. Because you can learn a lot of information just by doing ratios of quantities. And here's another one. The Earth is located at a distance of 1 astronomical unit from the Sun and orbits the Sun once a year. An Earth-like planet that is still at 1 astronomical unit around a star, but that star is 4 times as massive as the Sun, has a period of quarter of a year, half a year, 2 years, 4 years. So essentially what you do first is you identify the expression that relates all the variables in the problem. Ideally, not requiring you to plug in anything. So in this case, I would say the connection is Kepler's third law, where we said that this was a relationship between the period of the object going around the star, the distance between the object and the star, and the mass of the central object, be it the Sun, be it something else. So again, for the Earth, you could plug in numbers and get something here, and then you could look up the mass of the Sun, multiply it by 3 or 4, multiply it by 4, plug everything back into this expression, and get a new value for the period. Or I could say the square of the original period, which was 1 year, was 4 pi squared d cubed over gm. For the final setup, where the mass has been multiplied by 4, d has not changed, so I'll just write that as d cubed, but then the denominator becomes 4gm instead. The mass increased by a factor of 4. And now I just take the ratio of the two expressions. So I might say that the square of the final period divided by the square of the original period. So I essentially take the ratio of the left-hand side of those expressions. This is connected to this. And then this is connected to this. Then I just replace the equations as I see them. I could do a little simplification first. I guess these 4's cancel, so I could get rid of that. So then this is pi squared d cubed divided by gm. And then the original looks like it's 4 pi squared d cubed divided by gm. a fraction of fractions, usually the case with ratios. So pi squared d cubed gm, and then I flip the bottom one and multiply. So this is gm pi squared d cubed, and there's a 4 here. And again, behold, pi squares on the top, d cubes, g's, m's, all gone. The only thing that's left is 1/4, which says that the square of the final period equals 1/4 the square of the original period, which says that the final period equals 1/2 the original period. If the original period was 1 year, then this is just half a year. Increase the sun by a factor of 4 in mass, the Earth will feel a stronger gravitational pull towards it. If it remains in its same position, the only way it can do that and not fall and not miss the sun, and actually, the only way to prevent it from colliding and remain at 1 astronomical unit in a circle, is if its period shrinks down to half a year. Do I have another ratio question? No. But again, this is not just something that's unique to gravity. Let's see, an example of something, right, we said that the period of, right, suppose you have an object that is spinning in a circle, right, some mass that's going around at some velocity and some radius r away. I might say this has a given centripetal acceleration. If v doubles, and r does not change, actually let's make multiple things change. If v doubles and r doubles, then how does the centripetal acceleration compare to one another, to the original? In this case, the original centripetal acceleration was just v squared over r. That m is a little redundant, or rather it's not needed. The final centripetal acceleration is the final velocity squared, so in this case 2v squared, divided by the final radius, which is in this case just 2r. So this becomes 4v squared over 2r, or 2v squared over r. You might be able to reason out right away that the answer is it increases by a factor of 2. But if you don't see that yet, you could always do a ratio of the two. How does the final compare to the original? Take the ratio of the final to the original expression. So in this case, this is 2v squared over r divided by v squared over r. Fractions of fractions, so this is 2v squared over r. Flip the bottom, times r over v squared. The v's cancel, the r's cancel. You indeed get a that is a factor of 2. The centripetal acceleration in the final setup is twice the centripetal acceleration in the original setup. Ratios can be incredibly powerful if you hear them. Again, I would say this for this class as well. If you ever hear the word compare, I would suggest to think of it as an opportunity to take a ratio. All right, at the beginning of next class, I will wrap up gravity. I'll do an energy argument with gravity, an angular momentum argument with gravity to prove Kepler's second law, and then we'll be good to go. So then there's a handout also on Moodle how you would prove Kepler's first law. it would take too long for me to do in class. So there's a handout there. We've proved Kepler's third law, and I will show how you prove Kepler's second law in the next class. All right. Very good. And again, happy Halloween.